Hi, so welcome to class 2 for Theory of Equations course. In this lecture, we'll talk about mostly quadratic equations and their properties. We'll also be doing some examples and hopefully that should help. So let's look at the quadratic polynomial ft is equal to at square plus bt plus c. So what we want to understand is when will this have roots? So as you might have learned already, this can be simplified as ft can be written as a t square plus bt by a plus c by a, and we will complete the square here. So it will become t square plus 2b by 2a t plus b square by 4a square plus c by a minus b square by 4a square. And this gives us ft as a t plus b by 2a whole square plus 4ac minus b square by 4a square. So this is my quadratic polynomial. I have just rewritten it in this form by completing the square. So if you are searching for roots of f of t equal to 0, then therefore you can write a times this is equal to 0, which implies since a cannot be 0, if a is 0, this quadratic is no longer a quadratic and it becomes a linear polynomial, right? So if a is not 0, you have to have t plus b by 2a whole square is equal to b square minus 4ac by 4a square. Now taking square roots, t plus b by 2a will be equal to plus minus root over b square minus 4ac by 2a, right? So this gives us both the roots. T is equal to minus b plus minus root over b square minus 4ac by 2a, right? So one of the roots is alpha, which is minus t minus b plus root over b square minus 4ac by 2a, and the other root is beta, which is minus b minus root over b square minus 4ac by 2a, right? So we have found the two roots of the quadratic polynomial. Now we also can see very easily that alpha plus beta, if you sum the roots, notice that this part will get cancelled, the discriminant part. Sum of the roots is basically minus b by a, and product of the roots is equal to c by a, which is the Vieta relation for roots, right? So we have found both the roots, and we have found the relation between the sum of the roots and the product of the roots and the coefficients of the quadratic equation, right? Great. So now we can say that these roots are real if and only if the square root, this thing, is positive. So therefore we can find out nature of the roots here. Nature of roots for the equation, for the quadratic equation at square plus bt plus c is equal to 0. So alpha comma beta is minus b plus minus root over b square minus 4ac by 2a, and therefore if d, which is called the discriminant, which is b square minus 4ac, is greater than 0, alpha beta are real. If d real and distinct, if it is greater than 0, clearly the roots are not equal to each other. If d is equal to 0, alpha beta are real and equal, and if d is less than 0, then alpha beta are imaginary. So we'll also discuss a little bit of complex numbers in this video. So we'll come to the imaginary nature of the roots later. So let's try to understand this in a little more detail. If this can be written like this, if at square plus bt plus c has roots alpha and beta, you can also write this as at square plus bt plus c can be written also as a into t minus alpha into t minus beta, right? Because this polynomial also has roots alpha and beta, so they must be the same polynomial because they have the same two roots, right? Okay, so that is understood. Then we also want to discuss the graph of at square plus bt plus c. The graph of this looks like this. For example, if this is my y-axis basically, which is the value of y, and this is t, So if your t values increase like this, you have one root here, let's say, and this is one type of a possible graph of this function. So the graph is parabolic, parabola. This is the equation of a parabola, because as we completed the square, you notice that y was becoming a into t plus b by 2a whole square plus a constant term. So y is equal to a something square plus some constant is a parabola. So this you will learn when you do a little bit of coordinate geometry. But for now, we don't need to get into details. Just know that it is a parabola. I will draw the graph for y is equal to, let's say, we write ax square plus bx plus c. I'm resubstituting the variables. I'm changing it from t to x because this is what most people are familiar with. If you try to draw the graph of this, so you'll have two cases. Case one is when a is greater than 0. If a is greater than 0, the graph opens up upwards. So in this case, the graph can be either like this, or like this, or like this. So what are these three cases symbolizing? So here you have two real and unequal roots, right? So this is the case when d is greater than 0, and this is a is greater than 0 always. This is also a is greater than 0. This is also a is greater than 0. This is the case when alpha is equal to beta. So you have equal roots. So this is d is equal to 0. And d is what? D is b square minus 4ac are discriminant. And the final case is when d is less than 0, when there are no real roots. Because you notice that here the graph is always above the y is equal to 0 line, right? So these are the three different graphs for the equation when a is greater than 0. If a is less than 0, if a is less than 0, you get graphs which open downwards. So you can get a graph like this, you can get a graph like this, and you can get a graph like this. So this is all when a is less than 0, a is less than 0, a is less than 0. And this is for d greater than 0, d equal to 0, and d less than 0. Now, the graphs of this quadratic equation are important for you to know, because you will be able to solve problems like what happens if both the roots are less than 3, both roots are less than 3. Things like location of the roots you can figure out from the graph. So one thing you need to know here is the vertex of the parabola. Vertex of the parabola is this point, which is the lowest point in a graph if it faces up. So this vertex happens at the point x is equal to minus b by 2a. So if x is equal to minus b by 2a, you will realize when you put the values that the value of the parabola becomes d by 4a. If I'm not mistaken, either d by 4a or minus d by 4a. So you can check that out. Put the values and check whether it is plus or minus here. So that is the lowermost point. So this is also minus b by 2a. Alpha beta is equal to minus b by 2a. This is the vertex touching the x-axis here. And this is also minus b by 2a. Here, the lowest point is above y is equal to 0. So therefore, this has no real roots. So everywhere you should keep in mind that this, in case a is less than 0, you will have a vertex at a point which is the maxima of the parabola, right? These are maxima points, local maxima. So again, x will be minus b by 2a at the vertex. So this vertex point is important for you because sometimes if you have both the roots are bigger than some number, let's say 2, then you can say that minus b by 2a is greater than 2, right? Because root 1 is also bigger, root 2 is also bigger. So this point will definitely be bigger than 2. So we will use that to solve questions like find the condition that 3 is less than alpha beta is less than 5 for ax square plus bx plus c is equal to 0, where alpha beta are roots of this quadratic, right? So in this case, let's say your f of x is ax square plus bx plus c. So what you do is you take two cases. Case one is a greater than 0. So then the graph of the parabola can be like this, or like this, or like this, right? Now, if the condition is that both the roots are between 3 and 5, so you have 3 here and 5 here, you can also have this situation here, 3 and 5, But you cannot have this situation because discriminant less than 0 will imply there are no two roots. So in this case, he has said that there are two roots. So you have to have either this situation or this situation. Now notice that f of 3 is positive here, right? F of 3 is positive, f of 5 is also positive. So you can say f of 3 multiplied by f of 5 is greater than 0. Also, a is greater than 0 in this case. This case, a is greater than 0. So you can say actually f of a into f of 3 into f of 5 is greater than 0 for case number 1. And case number 2 will be when a is less than 0. The graph will be like this or like this. And if both the roots are between 3 and 5, you will realize again that f of 3 and f of 5 are both negative. So you can say that f of 3 into f of 5, since both are negative, still it is greater than 0. And in this case, now you can say a into f of 3 into f of 5 is less than 0 because a is negative, right? So writing these two conditions will help you solve for what is the condition on x basically, or ABC, for which both the roots are between 3 and 5. So basically the way to do location of roots question is always to draw the graph and see which of the graphs are possible, which type of graph is possible for that particular condition. We'll see one more case. Let's say you have an equation ax square plus bx plus c is equal to 0, and you have to say that one of the roots is between 2 and 3. One of the roots is between 2 and 3, right? So in that case, what you have to say is f of 2 into f of 3 must always be negative, right? Because f of 2 must be positive and f of 3 must be negative, or the other case is basically like this, when one of the roots is still f of 2 is negative now and f of 3 is positive, right? So always draw the graph for a location of roots question. And once you understand what the graph is saying, you will be able to figure out the condition for location of roots, right? So let's do some other examples. So one question that will help us understand another method is determine the values of x for which 6x square minus 5x minus 4 is always negative. So is always negative. I feel like this is pretty straightforward, but let's see. So 6x square minus 5x minus 4 is always negative. So now notice that this is a quadratic. So, pay attention to how I think about the problem. This is a quadratic and this is supposed to be less than 0, right? Always negative. No, now, for what values of x it is always negative is what we have to figure out. Now notice that the first coefficient, the a coefficient a is 6, is greater than 0. Therefore, the quadratic will face upwards like this, right? And it could be like this, it could be like this without touching, or it could touch also. There are three options for the upward facing quadratic. Now, what is the discriminant of this quadratic? Discriminant is equal to b square minus 4ac, which is 25 minus minus, so plus 4 into 4 into 6, right? So 25 plus 96, which is positive. If discriminant comes out positive, then that means that the graph has two real and unequal roots, right? This is the graph basically. I have rejected this graph and this graph because this was for d less than 0 and this was for d equal to 0. Now, if the graph of my function is like this, then I clearly know that my x values in between the two roots will give negative values of the parabola, right? So if my x is between alpha is less than x is less than beta, then f of x is less than 0, right? So this is my answer. So I just have to find the roots, right? So it will become, discriminant is root 121, which is 11. So roots are alpha beta is minus b, so 5 plus minus root 121, so 11 by 2 into 6. So basically 5 plus 6, 5 plus 11, 16 by 8, which is 2, or 5 minus 11, minus 6 by 2 into 6, so which is minus 1 by 2, right? So two of the roots are minus 1 by 2 and 2. So therefore you get minus half is less than x is less than half. That is the range for which f of x will be less than 0, right? So that illustrates how you have to think about quadratic equations. Think about them in terms of their graphs, and that will definitely help you solve many problems. One more question that we want to look at is this one. Determine the values of k, for which the equation x square plus x plus 2 by 3x plus 1 is equal to k is solvable for real x. Determine the values of k for which this is solvable for real x, right? So this type of question, always try to construct a quadratic. If it is a rational functions, try to cross multiply and make it into a quadratic. So x square plus x plus 2 is equal to 3kx plus k is what I'm getting after cross multiplication. So this becomes x square plus x common 1 minus 3k plus 2 minus k is equal to 0. So this is my quadratic, and this will be solvable. Solvable means real roots. So if it has real roots, then you know that what has to happen is discriminant is greater than or equal to 0. Therefore, you have 1 minus 3k whole square minus 4 into 2 minus k is greater than or equal to 0. Great. So this, how will you solve this inequality? So we'll simplify first. So 1 plus 9k square minus 6k minus 8 plus 4k is greater than or equal to 0. So this becomes 9k square minus 6k plus 4k. So minus 2k, and this becomes minus 7 is greater than or equal to 0. At this point, we can possibly factorize this minus 9k plus 7k, right? So we will use the wavy curve method to find the range of k. So we'll write 9k square minus 9k plus 7k minus 7 is greater than or equal to 0. 9k common k minus 1 plus 7 common k minus 1 is greater than or equal to 0. We have the factors 9k plus 7 and k minus 1, and it has to be greater than or equal to 0. So wavy curve method says find out the points where each of the factors become 0. So this factor becomes 0 at minus 7 by 9, and this factor becomes 0 at 1. So if it is above 1, if my curve k value is beyond 1, then this factor is positive and this factor is also positive. So the overall expression is positive above 1. If it is between minus 7 by 9 and 1, then this factor is positive because it's above minus 7 by 9, and this factor is negative. So this overall product becomes negative. And if the values of k are below minus 7 by 9, then both factors are negative. So overall values will be positive. So that is a brief example for the wavy curve method, which you might see in all standard books. So here the answer will be basically k can be greater than or equal to 1, or k can be less than or equal to minus 7 by 9. So my answers for k will be minus infinity to minus 7 by 9 included, union 1 to infinity. This is the range of k for which this equation is solvable, right? A couple of theory items that I want to discuss here is common roots. Common roots for two quadratic equations, it's a very straightforward thing. So let's say we have one equation a1x square plus b1x plus c1 is equal to 0, and another equation a2x square plus b2x plus c2 is equal to 0. Let's say both of these equations have alpha as a common root. Alpha as a common root. So if alpha is a root, then these equations must satisfy alpha. If alpha is put into them, then they become 0. So you have this situation here. So these equations are true. So what I will do is first I will eliminate the alpha square term and solve for alpha here from these two equations. So how to eliminate the alpha square term? I will multiply this equation by a2 and this equation by a1, and then I will subtract. So if I multiply this by a2, this becomes a1 a2 alpha square, and you subtract a1 a2 alpha square here. So that cancels out, and you get here a2 b1 alpha minus here you get a1 b2 alpha, and plus here you get c1 a2 minus c2 a1 is equal to 0. So therefore alpha can easily be solved as c1 C1 minus C1A2 plus C2A1 by A2B1 minus A1B2, right? Therefore, you have A1C2 minus A2C1 by A2B1 minus A1B2 as my alpha. So that is the first part of the solution. Now what you do is you do the same thing, but this time you eliminate not alpha square, this time you eliminate alpha, okay? So how do we do that? So let's write the two equations. And this equation is A2 alpha square plus B2 alpha plus C2 is equal to 0, right? Now to eliminate alpha, I should multiply this by B2 and multiply this by B1 and then subtract. And if you do that subtraction, you'll get A1 B2 alpha square minus A2 B1 alpha square plus C1 B2 minus C2 B1 is equal to 0. So basically alpha square becomes C2 B1 minus C1 B2 by A1 B2 minus A2 B1, right? So alpha square is coming as this and alpha came as this. So therefore, we can eliminate alpha by saying square of this must be equal to this, right? Because this square must become this because alpha and alpha square are there. So your condition for one common root is this. This square must be equal to C2B1 minus C1B2 by A1B2 minus A2B1. So you don't need to remember the condition. Don't try to remember this. What you should remember is how we got here. What we did was one time we took alpha as a common root, put alpha in both the equations. Once we solved for alpha, once we solved for alpha square by just eliminating the other variable, right? And once you do that, what you get is alpha is equal to something and alpha square is equal to something. And then equate alpha is equal to square the term that has alpha and equate it to the alpha square term and you get the condition. This is the condition for one common root. Condition for two common roots is obvious because if there are two common roots, the quadratic equations are actually identical. So if you have the same situation, a1 alpha x square plus b1 x plus c1 is equal to 0 and a2 x square plus b2 x plus c2 is equal to 0 and they have two common roots, then basically actually they are the same equation. So what you can say is a1 by a2 must be b1 by b2 must be c1 by c2. Only then can you actually say that both the equations are having the same common root. So the ratio of the terms must be same. So that is the condition for two common roots. So once that is done, what I want to quickly discuss is a little bit of basics of complex numbers. Basics of complex numbers. So what I will also put in the description of this video is links to much more detailed lectures on complex numbers. I have done that several times on my channel. So I'll not go into super detailed explanations here because you can just watch a series on complex number that is already available in my channel. It was done last year and actually multiple times I've done it. So you can find all of those videos there. What I will cover here basically is what are complex numbers. What are complex numbers? You have real numbers which are plotted on the real line here, real number line. Every real number basically can be put on this number line. You start from 0 here and you go this side, positive real numbers, negative real numbers. So basically the real number line is a one-dimensional representation of numbers. One-dimensional representation of numbers. Complex numbers, on the other hand, are basically you are going from one dimensions to two dimensions. So right now, if I have a y-axis also here, then technically you have the whole plane available to you, right? You don't just have one number line here, you have a whole plane. So whole plane means basically any point here can be given a coordinate x comma y, right? Any point can be given a coordinate. These points could be anywhere. All points have a coordinates, right? So every point that you represent x comma y can be now written in terms of a complex number. So each point in the two-dimensional plane represents a complex number, and the complex number that it will be equal to is basically x plus iy, where I is equal to root over -1. I is a constant, it is the square root of -1. If you're not understanding this, you should go back to the complex number lectures on my channel. I will link them in the description. X plus Iy is the description of a complex number. Now, there are some basic properties of complex number, and all algebraic properties that you are aware of are satisfied. So what you can do is you can add and subtract two complex numbers. So suppose you want to do this. So this addition of two complex numbers will be basically a third complex number called this I common y. Okay, I should have put plus I common y plus minus b, right? So this is my third complex number. Now each complex number, if you notice, x plus y iy is my complex number z. The real part of z is equal to x. The imaginary part of z is equal to y. The modulus of z, or written sometimes as mod z, is equal to root over x square plus y square. What does this mean on the real number on the complex plane? So any complex number z is here. It is x comma y basically. Its real part, this is the real part. This is the x coordinate, or equal to real part of z. This is the imaginary part. This is the y coordinate, or imaginary part of z. X and y are basically real numbers. And what is modulus of z? Modulus of z is this length. This length is called modulus of z. So you can see clearly by Pythagoras theorem, mod z should be equal to root over x square plus y square. What is the argument of z? Argument of z is basically the angle that this line makes with the positive x-axis. So you go anti-clockwise, and this angle is called argument of z. So you'll have tan theta is equal to y by x, and theta is equal to tan inverse y by x. This theta is called the argument of z, arg z, right? This theta is defined to be only between minus pi to pi. So minus theta is less than theta is less than equal to pi. This is called the principal value of the argument. Principal value of the argument. So what it means is it still covers, notice that it still covers all 2 pi angles. Principal value of the argument. How does it cover all 2 pi angles? It says that if you are in the complex plane, you can start drawing your angles from here to here. So angles from 0 to pi are allowed, and angles from 0 to minus pi are also allowed without including minus pi. So when you go in the clockwise manner, your angles are negative. Angles are negative if you go in the clockwise manner. Angles are positive if you go in the anti-clockwise manner. So you are still covering basically the whole of the complex plane, right? So basically what this means is any complex number can be represented in terms of x plus iy, where x is the x component here, the real part of z, y is this part, z mod z modulus is basically root over x square plus y square, or distance of z from the origin, and argument of z is the angle that this line, this distance, this vector line from origin to z makes with the positive direction of the x-axis. And principal value of the argument is defined to be the angle between minus pi to pi. So that is a little bit of basics of complex numbers that you need to be aware of. I will show you another important theorem in complex numbers, which is De Moivre's theorem. But before that, I will just explain what is polar form of a complex number. So polar form of a complex number is any complex number x plus iy can be written as r cos theta plus I into r sin theta. So what is this? So because any complex number z here, x comma y, is going to be written like this. So this distance r is called, r is equal to basically mod z. We have already discussed this. Let's say this angle is theta, my argument, right? So you can easily say that this distance, which was equal to x, is simply r cos theta, and this distance, which was equal to y, is simply r sin theta. So since that is true, x plus iy can be written like this, right? X plus iy can be written like this, and then x can be written as r cos theta plus I sin theta. So this is the polar form of a complex number. Now, where X and Y are basically R cos theta and R sin theta. R is equal to the modulus of the complex number. Now, because of Euler's beautiful theorem, where he derived that e power I theta is equal to cos theta plus I sin theta, this theorem was discovered by Euler in the 18th century. Because of this, now we can write this as R e I theta. Now, to get a sense of why this is true, you need to know Taylor series expansions of sine theta and cos theta. If you expand Taylor series expansions for e power x, sine x, and cos x, you will realize very quickly that e power ix will be cos x plus I sine x. So by a little bit of calculus and Taylor series, you can convince yourself that this is correct. However, we will not do that right away. We will just worry about this. Z is equal to R e I theta is called the Euler form of a complex number, So this Euler form is super useful sometimes, especially while taking roots of a complex number, because roots will be just division of the argument, right? So you have, if suppose you have Z1, Z2, right? Z1, Z2 are two complex numbers. You can multiply and divide them very easily using Euler's form. You can write e power I theta 1 multiplied by R2 e power I theta 2. It is equal to R1, R2 e power I theta 1 plus theta 2, right? So you can sort of get a sense of what multiplication is. Multiplication is basically a rotation of the complex numbers, where you get a new complex number of greater magnitude and greater angle. So I will just quickly draw a diagram and show you. Suppose your first complex number was Z1. This was R1 theta 1. So basically this length is R1, this angle is theta 1. Suppose your new complex number was, another complex number was Z2. This is R2. This angle is theta 2. This is Z2, R2, comma, theta 2. Your complex number which is combining Z1, Z2 or multiplying them will be R1, R2, e power I, theta 1 plus theta 2, right? So you have to add this angle and add this big angle. So you might get something like this, and you also have to multiply R1, R2, right? So my diagram is obviously not up to scale, but this length will become R1, R2 now. This is your product, and this total angle is equal to theta 1 plus theta 2. So multiplication is basically a rotation of the complex number by some angle and also a stretching of the complex number, right? So it's a transformation that involves scaling plus rotation. You can also look here. If you want to understand complex numbers in a little more detail, I recommend 3 Blue 1 Brown channel. He has wonderful visual representations of complex numbers, especially multiplication, division, and other operations. And also, I have already discussed this in far greater detail in one of my earlier lecture series on complex numbers. So I'll link all of that. You need to be aware of complex numbers because we'll be doing problems in quadratic equations where complex numbers are super useful in solving. Okay, so I will end at this point. I will bring you another video with a lot of problems. The next video basically will be a problem set that I will solve, and that will cover some typical theory of equations problems before we go on to the next set of exercises, the next set of theory. So the next set of theory will basically be cubic equations and higher degree equations and properties of polynomials. Those will be harder, but I will get you a problem set and I will solve that problem set in a video to illustrate what we have learned so far and where we can apply what we have learned so far in this course. Okay, so I hope you got something from this video. Definitely go forward and check out the complex number videos on the channel. They will be very useful for you. You should definitely look at them. I will link them in the description. So see you next time. I hope you enjoyed the video.